Mr. Nagabhushanam had a question about how do we select a medoid. Okay, I will explain, Mr. Nagabhushanam, with a very simple example, which is and it's also for the simplicity sake I will take a continuous variable. Okay, so now let me go to a previous slide. Okay, and let me do this. So let us say I have three objects. Mr. Nagabhushanam, you can see three objects A, B, C. Can you see them? I sometimes, okay, you can see. Okay, fine. So now can you tell me which is best candidate for a medoid? A, B, C, between A, B, C. I have not drawn it very well, but I hope you will give me B. Okay, very good, very good. Okay, but now this you can do it because you are able to see and you are able to visualize two-dimensional data, right? But many times you cannot visualize. In that case, what is the formula? So you take B and calculate some of the distances between B and A and B and C, and then you choose C and calculate the distance between from C to B and C to A, and then choose A, calculate distance from A to B and A to C, and then you compare all these three values, take the minimum one, right? Am I right? Mr. Nagabhushanam, is it understood? Okay, now you got it. But then you can know that it is very intensive computation. So that is why the K methods is challenging. Now let's start the hierarchical clustering. As we have discussed, the hierarchical clustering is that it's you have a objects belonging through a hierarchy into the clusters. So these are not like partitional, which are distinctly either you belong here or you belong there. So you can belong to this cluster, you can belong to this cluster, so on. So this object belongs to this cluster and also this cluster. This object belongs to this cluster but not to this cluster, so on. So now the hierarchical these clusters are represented best by these type of diagrams. This diagram where you have a 6 points, it is putting them into hierarchical clustering, and then it is drawing a dendrogram with those 6 points indicating where they join. So 1 and 3 are joining very early, okay, then 2 and 5 are joining little later, and then 4 is joining little later to this, and then so on. So these are the ways in which we represent a hierarchical cluster. So Mr. Nagabhushanam, you can see an example, okay, just to understand. So we can always say that this is, you never come across this in your business, but that's a different thing. You may have a similar situation and where you have to organize objects. So some of the characteristics is that you do not assume any number of clusters. Okay. So this is an important assumption which we did not have in K-means. So there we were forced to assume. And but you take the dendrogram and you can cut the dendrogram and you can get the desired number of clusters. So suppose I cut the dendrogram here. Okay, this cut, it is giving me 2 clusters, and this cut is giving me, I think, 1, 2, 3, 4 clusters. So by choosing the level at which you want to cut the dendrogram, you are going to get different number of clusters. And in one way, we are creating taxonomies through hierarchical clustering. A hierarchical clustering can take 2 broad approaches within it. One is agglomerative. Okay, the other is divisive. So agglomerative means that you have numerous objects. Each object you to start with represents a distinct cluster, and then you start merging those objects into a single cluster, and you continue it until you reach a single cluster. So this is to say, if you look at this diagram, you are in the agglomerative clustering. You are moving in this direction. Okay. So let me erase some of these lines. The agglomerative clustering is about this way. Okay, when you are going this way, and divisive clustering is this way. So what you are doing is to start with all the objects belong to a single cluster at this point. Then you can see that 6 seems to be far away from others. So you split 6 into a separate cluster, you end up with 2 clusters. Then you realize that some more objects are far off, and you keep on dividing the objects, and then you're going to get different clusters. So, so what do you do till until you get each point in a different cluster? You continue that. So agglomerative, you keep joining the objects and combining them. Divisive cluster, to start with all inclusive cluster and keep splitting it at every point. So the hierarchical algorithms can use either similarity matrix or a distance matrix, and the merge or split is done one cluster at a time. So we look at agglomerative clustering algorithm. So first thing we need to do is to compute proximity matrix or or distance matrix. Then we say that each data point is a cluster, and then we start merging two closest clusters, and then update the proximity matrix again, because for example, when we had 3 objects, to start with, let's say we have 4 objects to make our life easy. So we will be having a matrix which is representing every possible combination distance. So it is a 4 by 4 matrix, but then it will be a triangular matrix to represent the distance between these 4 objects. And first thing we did is that we have checked the proximity matrix and we merged these two. Okay. Now we have 3 clusters, but the distance between these two is not affected. Okay. But what about the distance between this point with this point? Because this point no longer exists as a separate cluster. So let's say A, B, C, D. A, B have been merged. So there is nothing like a distance from A to D or B to D. So we have to define a new distance from D to the cluster AB. So we have to update the proximity matrix because we have lesser number of clusters now. Previously we had 4 objects and 4 clusters. Now we had reduced those 4 clusters to 3 clusters. So we need to update the proximity matrix. And so we can see that the distance of C2A and C2B has to be updated because we need to convert this into a single distance. And similarly with the D, we have to do that, but the distance from C to D is not impacted. So we keep repeating this merger until a single cluster remains. So the key operation is that we have to repeatedly compute the proximity matrix and proximity of the 2 clusters. So effectively what it means, how do we calculate the distance of these distance between the clusters as opposed to distance between the objects. So we need some situation, some techniques, so we'll look at them. So to explain it little better, suppose that we have 12 objects. To start with, each of them is a different cluster. So the P1 to P12, so we have a 12 by 12 proximity matrix. But what happens is that as we execute the agglomerative hierarchical clustering, we may reach a point where P1, P2 join to create one cluster, P3, P4 join to create another cluster. So finally, we ended up with 5 clusters to represent those 12 objects. So the proximity matrix is reduced to 5 by 5 matrix from 12 by 12 matrix. Now, so again, from 5 by 5, we have to further merge. So let's say C2 and C5 are to be merged. So then what will happen? This has to be reduced to this 5 by 5 matrix has to be reduced to 4 by 4 matrix. How do we do that? We combine C2 and C5 have to become one. Okay. So what it means that the shaded region, I hope you are seeing that shaded region belongs to C2 or C5. That has to be merged into single values. So that is C2, C5 have a single distance from C1. Similarly, C2, C5 have a single distance from C3. C2, C5 have a single distance from C4. And the distance from C2, C5 has to be reduced to 0 because they have become a single cluster. So how do we calculate? Mr. Nagbhushan will come to that. Whether we take midpoint or we do some other technique, we'll come to that. But the concept is that we need to treat them as a single cluster. So we have to have a technique to reduce the matrix size. So there can be several ways to measure the intercluster distance or similarity. Let us say there are two clusters, cluster 1 and cluster 2. Okay, we are seeing this is one cluster and this is another cluster. And each cluster has, say for arbitrarily we have chosen them have a 4 points each. How do we calculate the distance between these clusters? On what basis? One can be minimum. So I can see that this is representing the minimum. So this can be taken as the distance between the clusters or the similarity between the clusters. Or I can take the maximum. There is some reason why we may want to choose the maximum. Or I can choose the group average. Group average is that I can calculate the distance of every object in C1 to every object in C2 and I take the average. Or I can calculate a centroid of C1 and centroid of C2 and I can do the distance between the centroids. Or we may choose some other objective function. So now the point is there are several techniques that are available when we want to define the intercluster distance or similarity. So let's look at how does a minimum look like. How does a maximum look? How does a group average look? And the centroid is not available, but the centroid is representing in this. Okay, let me show the centroid. This is the distance between the centroids. My diagram is, it's not a straight line, but I hope you understand. These are the two centroids for the two clusters, and we are looking at the distance between centroids, which is pretty much somewhat has some similarity with our k-means approach, which is always based on the mean, which is for a continuous value. So the center. Now let's take an example and solve the clustering problem. So we have 6 points and we have taken two-dimensional objects. Each point is a two-dimensional, so we can represent that on a graph. So we have P1 to P6. They have been plotted on the graph, and we have also computed the distance of each point to the other. So we can see that it is we only need the diagonal matrix. So we can compute, we can look at either upper half or lower half. We don't need to worry about the rest. So now we got every information, so we can proceed to create the clusters, hierarchical clusters among the 6 objects P1 to P6. So now let's, since we are here, let's observe something. Let us see which are the closest points in the among the all the objects. It is simply observing the matrix, is it not? So this seems to be the closest. 0.11, right? There is nothing smaller than that. So P3 to P6 seems to be the closest. Then farthest seems to be P1 to P4. Okay. And others, next closest seems to be P2 to P5. P2 to P5 seems to be next closest. Okay, this distance. And then we have P2 to P3, which is the next third closest. So what is your question, Mr. Nagabhushanam? You have asked any question or not? Okay, fine. I think it is the C2 to C5. You have a doubt about C2 to C5 in this case, or this is about the previous cluster? Okay, I'll proceed further. Now, okay. So we'll take this and we will take the minimum approach and we compute the clusters. So we can see that the first thing that gets joined is 3 and 6. Okay, this is the shortest distance. And then you can recompute the matrix. What happens is that we are taking the minimum approach. So 3 and 6 related, there will be a change. So we will see that P1 distance from P3 to P6, the minimum distance is coming from P3. So this will be taken, and this will be avoided. So P2, again, this will be avoided. Then P4, distance from P3 is this will be avoided. 6 will be avoided. P5, same thing. Okay, 6 will be avoided. So now it is easy to compute the distance. From this 6 by 6 matrix, we need to convert it into 5 by 5 matrix. Mr. Vivek, just give me 1 minute. I will unmute you. Mr. Vivek, what is your question? Mr. Vivek, I have unmuted you. I'm still not able to hear you. I'm not able to hear you. I'm muting you again. I have not understood your question. Maybe you want to explain it again. Okay, Mr. Neeraj had asked a question in Q&A. The Mr. Neeraj's question is whether there will be some questions with respect to R in the examination. No, no. R, as we have discussed several times, we will focus only on data mining. If some of you are good with Python and don't want to learn R because you are already good with Python and you are already able to solve, so why should I bother you with? Because you can. Our intention is to learn data mining, not a specific language. But I will demonstrate the task as much as I can in R because I have to choose one. I can't demonstrate in every language. Okay, the question from Mr. Vivek is that P3 and P4 and P2, P3 both are 0.15. Yeah, okay. So when such a challenge comes, we will have to overcome it, right? But that is our intention is we are still in the first step. So where we had to merge P3 and P6. Okay. So P3 and P6 have been merged, and then we have recognized that now we needed some values. So we need to reduce the matrix. So we will maintain the distance from P1 to P3, P6 as the same as distance from P1 to P3. Similarly, distance from P2 to P3, P6 is same as distance from P2 to P3. Distance from P4 to P3, P6 as same as distance this. Then P5 also same because luckily 6 is somewhat a outward looking object. So the 3 could dominate the. So now we have to essentially we need to reduce this matrix to a smaller size. So it is 5 by 5 matrix. So we are telling which are the objects we'll keep and which we will remove. Now next point will be that we need to find the next smallest distance. Next smallest distance is P2 to P5. So the next cluster that we will recognize is P2 to P5, right? And after this is merged, again we need to recompute that matrix. So interestingly, 5 is outward looking and 2 is inward looking. So now the calculation will also again be we have to recompute distance of P1 to P2, P5. So we are going to keep this and P3 to P4 to P2, P5. This is going to stay. So we will reduce. So that way, and then the next one will be we will have to compute the distance of what is not merged yet. Okay, so we have 1, 2, 3, 4. So we need to look at the distance. We can see that the distance between these two, cluster 1 and cluster 2, will be smallest because it takes the minimum approach. So it considers 2 to 3. So 2 to 3, the side distance is 0.15, which is the nearest smallest. So next merger cluster will be happening here, which is a merger of this cluster and this cluster, which is we are creating a new cluster 3. Then we have 3 clusters. One is representing 2, 3, 5, 6. Then one is representing 1 and the other is representing 4. Then we will see that next cluster will be merging the 4 to this existing cluster and 4 to 3. That will create the cluster 4. So this is what is happening. Finally, the 1 gets joined. So here at this point, we have a single cluster. So that completes the agglomerative clustering using the minimum distance. Between intercluster distance is considered based on the minimum distance among the objects within the cluster. So I hope that is clear. So if we take the approach instead of minimum, okay, now let's look at what is strength of the minimum. It can handle non-elliptical shapes, so that can be one. And limitations of the minimum. Obviously, we are looking at minimum distance, so a noise point can play a significant role. Okay, so that means the because of the noise, we are ending up with a cluster which is of very arbitrary shape, while a natural cluster would have been something like this. Now let's look at using the max. So now let's also look at why should we ever bother about max. Let's take three clusters to understand which are the nearest distances and how do we find out. Let's say there is one cluster which is of the shape of this, another cluster with the shape of this, and a third cluster. Now we want to find out which is the closest cluster from one. There are three clusters: cluster 1, cluster 2, cluster 3. Somebody wants to tell me which is the closest cluster to 1. Is it 2 or 3? Anybody wants to answer? You want me to swallow the question, give the question and give the answer? Okay. Okay, somebody has. Oh, fine. Mr. Rajiv has answered. The cluster 2 is closest to cluster cluster. Okay, this is an interesting observation. Say Mr. Rajiv made an observation that cluster 2 seems to be closer to cluster 1 rather than cluster 3. Do everybody agree with that? Do everybody agree that cluster 2 is closer to cluster 1 than cluster 3? Okay, there is a Miss Harshini pointing out cluster 3 seems to be closer. Yes. In fact, the point is that if we take the weighted sum or the distances, okay, I'm sorry. If we look at the distances, no, 1 is not a subset of 3. 1 and 3 are two different clusters. So all we were saying is, so the point is that the if we take the minimum distance, the 1 will come as very close to 2. If I take the minimum distance, 1 and 2 will come very close. But if I take the centroid, 1 and 2 will be far off. Actually, 1 and 3 will be closer. And if I take the maximum distance, 1, 2 will be very far. Actually, the 1, 2 will be considered very far, and the 3 is relatively stays close. So the point is depending on the cluster shape. So the types of distance consideration can be can make a meaningful difference. So in general, we have the techniques which are based on various choices, minimum or maximum or average or centroid. If we choose the maximum, the sequence will be different. First cluster will be still same. Second cluster will still be same. But the third cluster, instead of, because we are not looking at the cluster between 1 and 2 is not decided by this, rather by this. So what we recognize is that the 4 will become closer to 1. So the third cluster will be this. Okay. Similarly, the fourth cluster, when we are looking at, because we consider the maximum distance, because once we make this as a cluster, so we need to compare 1 to 5 and 1 to 4, which is representing the maximum distances. So fourth cluster will include 1 with 2, and then finally we are going to get the final cluster, which is combination of all. So we can see that the dendrogram is very different. So 1 is getting created and 2 is getting created quickly, but later on things are changing. Third cluster is happening by join of 4 with 3, 6, and then fourth cluster is happening by joining of 1 with 2, 5, and then all of them are joined. So what is strength of the max? It can handle the noise better, because when you are looking at the maximum distance, the impact from the noise will be less. So that is one strength, but it tends to break larger clusters. It can't handle the clusters which are of highly distinct sizes, because it is looking at the maximum distance, so it is breaking them up. As you can see, the maximum distance in this natural cluster is much higher than this natural cluster. But then in hierarchical clustering, all the objects are distinct till they are merged. So what it means that the merger is not going to happen, because this distance will come out to be much higher than the distance from this point to this point. If we take the group average, the clustering sequence will be 1 and 2 remains the same. Later on, we will have the 4 joining 3, 6 to create 1. But then after that, the 1 will be joining 3. The point 1, object 1 will join this, and then finally this will join. So group average will lead to a different dendrogram. So that is you can see the comparison of when we use different techniques, we are going to get different agglomerations to create the clusters. So given a data, we need to observe, we need also to check what is the technique that we would like to use, and accordingly the solution can be different. So min and max are easy to compute. They are very easy to compute. This is a little challenging. So unless the data is small, this can be challenging. We have looked at agglomerative hierarchical clustering. Now what we do is we look at divisive hierarchical clustering. So divisive hierarchical clustering is that to start with, all the objects are taken as belonging to a single cluster, and then we start splitting the cluster into smaller clusters, and we continue the process of splitting until we have each object in a different cluster. So how do we go about doing this? Is when we have these 6 objects, which are the same set of objects that we have done for our agglomerative clustering, what we do is that we build a minimum spanning tree. The logic for minimum spanning tree is very simple. Among all the distances, look at the smallest distance, connect. Okay. Then look at the next smallest distance, connect. I think 2, 5 is next smallest. Then look at the next smallest distance and connect. So it's simply, and unless an object is separated, we keep on connecting, and the moment the object is connected to at least one other object, we don't need to worry about that. So this is going to form a minimum spanning tree. So in the minimum spanning tree, so we can look at how to build the minimum spanning tree. Then what we do is that we will start splitting. So once we have the minimum spanning tree based on the proximity, then what we do is repeatedly we keep creating a new cluster by breaking the link that corresponds to largest distance or the smallest similarity until we get all singleton clusters. So in this case, so we start looking at the maximum distance. We have two clusters, one cluster represented by this, another cluster represented by the rest. Then we have the next highest distance, then the next highest distance, then the next highest distance, then the next highest distance. So we keep on breaking it so that in sequentially we start creating, we keep on adding a new cluster. So we start with one cluster and keep on breaking it until we get each object into a distinct cluster. And we have a more complex solution for hierarchical clustering, which is a chameleon algorithm. So this algorithm works with uh, a k nearest neighbor concept. So previously we built a minimum spanning tree. So what we did was that we joined each object to the nearest neighbor. Instead of that, chameleon, what it does is that it connects each object to the k nearest neighbors. Once we do that, what we get will not be a minimum spanning tree, but we get a graph. I hope you understand the difference between a graph and a tree. A graph can have a loops and multiple ways to go from multiple joins from the objects. So, but a tree will not have that. Tree will have a essentially no loops, and so here once we had connected to one nearest neighbor, we had a minimum spanning tree, but we connect to k nearest neighbors, that k can be 2, 3, 4, whatever. Then we are going to get a graph, and then what we do is that we have the data set and we can construct this k nearest neighbor. In this case, I think they use k is equal to, I think they used a k is equal to only 2 in this case. Now, after we have this, what we do is that we start cutting the partitioning the graph such that the edge cuts are minimized. So we cut here to start with So we see that only 3 edges had to be cut to split this into 2 clusters. And then we also look at the weights associated with each of these clusters, edges. So thereby, we want to minimize the edge cuts so that the 2 clusters that we create are compact, and at the same time, the so we essentially we are minimizing the weights of the edge cuts because we are creating each edge is representing the so essentially we want to have a compact clusters which are connected with as many objects as possible. And so by saying that we are looking for points where there are minimum connections and then removing those connections, so that ensures that the clusters are compact and well connected. So the nearest neighborhood is considered. So we are not only considering its proximity to nearest object, nearest k objects. So if it's k, it should stay whichever side it finds its k nearest neighbor. So that is the concept. So this is a far more complex algorithm to implement. And if we want to do the computation, so it will take far more time, very large time, unless we take the extremely simple case. In that case, we don't see the complete effectiveness. But then this can be used when we want something where we recognize that neighborhood not only involves connection with any one object, but with the many objects in the neighborhood. So let's look at the complexity, time complexity. So it is the first thing is to compute the proximity matrix. We need a n square, so that is order of n square. So if we have 10 objects, the number of computations are of the order of 10 square. It's not exactly 10 square, it will be 10 square by 2, less than 10 square, but of the order. So it is non-linearly increases with the number of objects. And we need to repeatedly compute the proximity matrix. So once we merge, we make one merger, the size of the proximity matrix reduces by 1. Previously it was 10 by 10, it becomes 9 by 9. But then we need to recompute many of those calculations. So we need to do them n times. So what it means is that many times the order comes to n cubed. And by using some techniques, we can reduce it to n square log n, but still it is far more resource intensive, and it takes far more time than k-means algorithm for a given set of data objects and dimensions. What is the challenge with hierarchical clustering? Once a decision is made, we do not undo it. In case of k-means, we are shifting the mean and then we are recomputing to which mean the objects belong. So thereby we are changing the shapes of the clusters. But in this case, we do not do that. And there is no objective function to directly minimize. So that is the reason it ends up with some problems like one of the approaches creates sensitivity to the noise. Some of the approaches have problem with the size and shape, and some of the approaches have problem with sizes of the larger clusters. Okay, at this point we take break for a couple of minutes.